Let's talk about data-centric. You heard my introduction, and you know that I'm a holistic software architect. I do a lot of different things. I live somewhere at the intersection of magic and technology. And we have a problem in our industry that has been compounding. And the approaches that we're taking are not scaling, and they cannot keep up. Moreover, we are entering this age of AI. But what makes our AI valuable is the data and the information that it is trained on and that powers the answers and the interactions that it gives us. And the solutions that I'm going to talk about solve so many problems, but it is a new way of thinking about this. And so a lot of what happened started in 2017. There was a group called the Semantic Arts, and they published yet another manifesto. We had the Agile Manifesto. We've had a number of manifestos over the years. They published the Data-Centric Manifesto, and they started with this. We have uncovered the root cause of the messy state of information architecture in large institutions and on the web today. It is the prevailing application-centric mindset that gives applications priority over data. The remedy is to flip this on its head. Data is the center of the universe. Applications are ephemeral. And I've mentioned the Data-Centric Manifesto a number of times this week, and it came up in my talk yesterday about REST, because a lot of these ideas start to overlap and they start to build on each other. And this is truly a monumental challenge that we're facing. And we have tools that work, but they're not scaling. And I want to put this in perspective. So I'm going to start for a moment with the history of information technology, because we have a lot of potential that can be realized as soon as we let go of this antiquated notion of the machine. So it goes back to an era when the definition of a computer was not what we know of today. If you looked it up in a dictionary 100 years ago, the definition of a computer was one who computes. It was an occupation. It was a job title. You could be a doctor. You could be a lawyer. You could be a dentist. You could be a cobbler. You could be a computer. And these were people. And computation, being a computer, it was considered semi-skilled labor at best. And this was best exemplified in the fantastic film that came out a number of years ago called Hidden Figures. And it tells the story of a number of computers, the human beings who did the calculations. This is a montage from that film.
Not many computers last more than a few days. He's been through a dozen in as many months.
Excuse me, ma'am. Mr. Harrison's computer report. Take the desk in the back. I'll get you working in.
What's the status on that computer?
She's right behind you, Mr. Harrison.
Computers don't author reports.
Mary, a person with engineer's mind should be an engineer. You can't be a computer the rest of your life.
I have told you this. Computers don't author reports. Fix it.
Those are my calculations. My name should be on.
That is not the way this works.
So if you've seen this film, one of the pivotal points of the film was when NASA finally got a computer by our definition. But it wasn't a computer. It was a machine that displaced the computers. It was a data processing system. It was supplied by IBM, International Business Machines. And like so many technological innovations during the Industrial Revolution, machines were built to automate and streamline human labor. And even the digital electronic ones that were supplied by IBM, this idea of machines. Now, my very first job, I was an intern when I was still in school, and I worked at a university, and I worked in what they called the machine room, because that's where the machines were. Of course, we probably call it a server room or a data center today. But like any automation or labor-saving machine, computing machines were built for the longest time with narrow purpose of automating one specific type of computation. This is a machine that will compute the tides, because it was quite tedious to compute these by hands if you've ever tried to do it. This is a machine that calculates the positions of the stars and the planets. This is a machine that will calculate the initial rotor settings for a 3-rotor Enigma machine. These were machines that solved a problem. And every time we had a new problem to be solved, we designed and we created a new machine, because the tide machine can't calculate the next solar eclipse any more than the cotton gin can manufacture glass bottles. And creating new machines, every time we had new requirements, it was time consuming and it was expensive. But what if we didn't have to? In 1937, Alan Turing wrote a paper called On Computable Numbers and the Einstein Problem. I think I said that right. 1936. I was off by a year. Einstein's problem. The decision problem. And it was in this paper that he conceived of an entirely new machine that could compute the tides, or compute the positions of the planets, or any other computable problem. It was a radical new conception of machine that everybody dubbed the Turing machine, because it was a very special kind of machine. It was a general purpose machine that could be reprogrammed instead of being redesigned and rebuilt. And it was a revolutionary idea. Now, just 6 years later, the ENIAC, which was one of the first programmable computers that existed, it was a general purpose electronic machine. It started to become feasible to automate more and more of the work that human computers were doing. So when we needed to compute the trajectories of missiles, we would feed raw data in, and instructions and process data would come out. And likewise, when we needed to do the necessary calculations to make sure that a nuclear fission chain reaction wouldn't, accidentally ignite the atmosphere and wipe out all life on this planet, we gave it a different set of instructions and process data came out. And this is kind of exemplified by this XKCD comic, when they're like, okay, if we got the math right, then this is going to be amazing. But it's possible we made a mistake and the heat will ignite the atmosphere, destroying the planet in the cleansing conflagration. And one of the engineers says, wow, okay, question, just to double check, although I'm 99% sure, is it SOHCAHTOA or is it SOHCAHTOA? Oh, for the love of, can someone please redo Steve's work? I don't want to do the test anymore. And see, these machines, they were not only faster, but more consistent and less prone to errors. So essentially, these were time and labor-saving devices. And these are machines that didn't deal with information, just data. And so the context was added by people with domain knowledge, because as you saw in that clip, it wasn't typically part of the computer's job. And so as storage got cheaper, compute got cheaper, we could add more business rules and more context, and that led to the first information systems. And like the early machines of Turing's era, today's information systems are typically built with narrow purpose. We build a new machine for every set of problems. We have a warehouse, well, we'll build a warehouse system. We have a human resources department, well, we'll create an HR system. We have payroll, we'll create a payroll system. We have accounting, we'll create an accounting system. And we build machine after machine after machine after machine. But what we're finding today is that the most pressing business problems that we need to solve rely on answers that can only be determined by combining information from multiple information systems. But the nature of these machines that we create, it makes them more like information silos. Everything's walled off, it's boxed off. And so we created new machines in the form of business intelligence tools and reporting frameworks. But ultimately, the data without the code is meaningless. So long story short, the way we're building software today, it makes it extraordinarily difficult to connect the information that's scattered across all these silos. And even with AI and everything else, in fact, especially in this era of AI, we have problems that we need to figure out how to solve, this next generation of problems. Modern enterprises face pressure to swiftly adapt to dynamic markets. However, the crucial knowledge to power such evolution is typically spread across different sectors of the organization, managed by fragmented information systems that are difficult to integrate. This situation obstructs a clear understanding of the business's health, its core challenges, and potential opportunities for innovation. So the consumers of these applications need access to connect the information within these silos. One of my clients came to me not that long ago with this exact problem. What they needed to do was answer this question. What do I currently hold in my warehouse that isn't a current product or used to manufacture any of our current products? In other words, what's in the warehouse that's just taking up space? And it's a hard problem to solve just by walking around that warehouse. So we have to look at a couple of systems. They have a part lifecycle management system. They have a PLM. They have a warehouse system. What's in the warehouse? They have a sales system with what it is they're selling. They have a product catalog. And what we need to do to answer that question is we need to connect all of these, because the answer to that question is scattered in these silos. So what do? How do we solve this problem? Well, typically, we'll build yet another application silo. Or we'll write one more custom machine to go and get this data and then add all the context to it, not all the meaning to it, not all the business logic to it, and that data and that data and that data, and we'll hand write all of this integration code and all of the business rules, because the business rules are locked not in the data, but in the code. And that code is not portable, so we've got to recreate all of it. We've got to do all of this by hand. This is one of our defaults. And how long does it take to build one of these things, and how long does it take for the business to think up another one of those questions? And for a while, we tried things like data warehouses. Well, what if we had one silo to rule them all, if we put everything into there? And this was a good idea, except it never was. The dream was a good idea. The reality never was. And this is before we had a concept of what we now call big data, where this just falls apart. And it's still a mess of data integration apps. And the code is brittle, it's repetitive. And then the business comes up with a new question, with something that doesn't exist in your fact and your dimension tables. Based on our current delivery commitments, inventory and procurement lead time, what sales deadlines are in danger of shipping? We need to know this. So this involves the PLM, the warehouse, the sales database, the procurement system, the product catalog, the supplier catalog, which is external, the supplier inventory, which is external, the shipment tracking, which is external, and the production lead times, which are all external. Now I have to extend my data warehouse. Now I have to build yet another ETL job, and all these things again and again and again. And don't forget, every supplier has different data models. They identify all these things differently. They've got different terms, different semantics, different custom interfaces, all of this. And so what we've been doing so far to try to optimize this problem is just dump everything into a data lake in kind of a flat, extensible format that we could go and write code again to go and put these pieces together, write these distributed stream jobs and query jobs and things like that. And we can do this. Now, the data lake has value. I'm not advocating throwing it away, but the thing is, all of these approaches are struggling to keep up with reality. And what we're talking about here is what the Semantic Arts, what the Data-Centric manifesto talks about as the application-centric paradigm. And they said this: we believe that the current enterprise information system paradigm centered on applications with data as second-class citizens is at the heart of most of the problems with the current enterprise systems. Can we do better? And the answer is yes. We don't have to always think about point-to-point integrations. Like just this handful of systems with these point-to-point integrations, you have 500 apps, that's 124,750 integrations. The data-centric approach is you have 500 apps, 500 silos, and 0 integrations. What's this purple thing? It seems like cool things are happening with that purple thing. The purple thing is the data in a form where it just connects. It just works. And this happens when we think of the data not as a function of the application, but as the fuel for the application. Because I'm sure almost everybody in this room has retired an old system. And what is the first thing that you do when you replace an old legacy system with a new one? Figure out how to migrate all the data over. Because we'll throw those applications away, but that data is still relevant. That data still matters. We have all the tools, we have the technology, we have everything we need to address this. We just have to change the way we think. So what are the principles of this manifesto? If they're going out there and saying, you know, we believe, this is our manifesto. 5 things. Let's go through these. Number 1, data is a key asset of any person, organization, or society. Right out of the gate, I'm going to be honest with you, I'm not sure I fully agree. Let me explain. We talk about data. How many times do you hear companies say this? We're data-driven. We like to make data-driven decisions. It's all about the data. Data is the new oil. Data, 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 data. Okay, you make data-driven decisions. Here's some data. What should I do? It's not about the data. It's about the information. Information is data with context. Now, some of the context is expressed, some of it is inferred. Like, this is probably not Celsius. If it is, on Thursday, probably Wednesday, I'm going to die. And then as a human, we have to look at that and figure out what that really means. But we've got some context here. And then we have knowledge. And this is what we want. We talk about artificial intelligence, but it's not intelligence. Not as we understand it, not as humans express intelligence. It's clever, it's useful, it's valuable, it's neat. But it's still only capable of sort of inferring certain rules at certain times, and not with all of the context, only the context that exists at its training set. Knowledge is multiple contexts. And these rules and these axioms and these ways of thinking about doing this, it's the multiple contexts that allow for informed decisions. So now I know that on Tuesday I should wear a jacket. I know that on Thursday it would be a good day for a bike ride. It's this that allows me to make decisions. It's easy for us humans, it's difficult for machines. But having a human in the middle, it's too slow. It works, but it's too slow. And the reality is data is not information, information is not knowledge, and knowledge is not understanding, and understanding is not wisdom. But data is the core of so many things. There's a reason that there is an entire economy based on our data. They deal in our attention because it allows them to gather our data. There are multi-billion-dollar companies that have that valuation because of our data. Our organizations live or die by their data or information. So absolutely, data is that key asset. What about number 2 and number 3? Data is self-describing and doesn't rely on the application. This is a radical departure. Because if we ever want to use that data, we get it from an application, and yes, we get JSON or whatever, and we look at it, we look at documentation, and then we hand code all of the rules. We hand code all of the meanings. We hand write all of the mappings that, hey, in my world I say this, in your world I say that, so I'm going to connect these with a line of code. Oh, you changed something, my code just broke. But this is the status quo. And data is expressed in open, non-proprietary formats. This is sometimes, not always. But like I said, we're at this weird inflection point where the volume of data that we are creating is going up exponentially. But the way that we're trying to work with the data is following this very shallow linear line. These two lines, they are not going to converge anytime soon. The way that we're doing this is a losing proposition. The Semantic Arts folks also say this. We further believe that the main barrier to changing this paradigm is not technical, but mental and inertial. Like I said, we already have the tools, the technologies, and the standards to address this. We just need to change the way we think. So what does this data-centric world look like? And why is it so different to what we're doing? And how is it going to solve the problem of exponential growth in data, but not exponential growth in our ability to work with it and apply meaning to it and do all of these things? Well, let's look at the data-centric stack. And the most prominent approach starts with the ideas and the architecture of the World Wide Web. And we know about the World Wide Web. It was an attempt that started in 1989 when Tim Berners-Lee wrote a proposal to try to connect the world's information. And he understood that, yeah, this is a little bit of a radical idea. In fact, when he gave this proposal to his boss, he didn't hear anything back immediately. And they eventually found this memo, the original copy of the memo he gave his boss in his boss's personal effects after he passed away. And on the top of this, he handwrote these words, vague but exciting. And I don't think we're at a place anymore where this data-centric approach is vague anymore, but it is exciting. And he knew that it was going to be slow at first. He knew it was going to take time for these things to catch on, but once they do, these ideas have their own exponential growth. He said the result should be sufficiently attractive to use that information contained would grow past a critical threshold, so the usefulness of the scheme would in turn encourage its increased use. And as we do this more and more in the organization, it only accelerates. We're talking about network effects. We're talking about the idea of Metcalfe's law that the value of a network is proportional, I think, to the square of the number of nodes in the network. That if I'm creating a telephone network and I can call only one person, it's not a very valuable network. But at some point, it reaches a critical mass, and then everybody is on that network. And now it's super valuable because I can use that network to call anybody. And all of this data-centric stuff starts with the ideas of the World Wide Web. And as revolutionary as the web was for information, the data-centric approach is going to have the same level of revolutionary impact to how we think about data. So the next piece is this idea about rest. And this is one of the reasons that even in the year 2024, I'm coming to a conference like this where people are talking about the most cutting-edge things. And then yesterday I was talking about rest, which is 25 years old by its definition, and it's the architecture of the web, so it's closer to 30 years old at this point. And we think of rest as moving data around, but the reality is it's working with information. Rest starts with this idea of the resource abstraction, and it's a way of identifying entities and concepts and terms and ideas. We're using stable network-friendly identifiers. These are URIs, and it gives us all kinds of interesting capabilities. Now, if you have conversations about REST, one of the things you're going to see is people are going to look at your RESTful API and they're going to do one of these. They're going to be like, excuse me, that's not REST. And we get into like really pedantic debates about how our URIs should be. And like any of these kind of all broadly fall into the category of REST APIs. But what we're trying to do is we're trying to assign identifiers to these meaningful concepts, to these meaningful things that are stable, that don't change. And so the problem with something like this, API v2 get person by ID, I'm not identifying a resource, I'm identifying a function, and I'm putting the representation of the result in the identity of the thing. So when the representation changes, the identity changes, and that breaks any attempt to automatically start to connect these things together. So here we are, we're in a situation where maybe we're doing things closer to this, where we have stable identifiers, we've decoupled representation from identity and implementation and everything else. We've got this type of identifier, and we're passing JSON back and forth. We've got stable API, strong things, but we're still dealing with data and not information. But what does that mean? Well, the web was about moving information around, and this is just moving data around. This is an information resource, and I am a non-information resource. But we start looking at this, and data is supposed to be self-describing. I mean, I have human-friendly labels, but they don't mean anything, right? 3 times I have the word title. And 3 times I mean different things. Here I mean the title of a book. Here I mean a nobility title. Here I mean a job title, but we all call it title. So there's nothing self-describing in there. We have an issue with semantics. And there was a great slide from a presentation from AWS about this. And the first thing is we think JSON is easy to understand. It's not, right? We just think it is. A friend of mine, Brian Sletton, often says, JSON is a lie. It lies to you. It tells you that the nuances of reality can be expressed simply in decontextualized name-value pairs, and that can be meaningful. It hides the complexity of the real world that we live in. People say, my data model is just JSON. Well, JSON's not a data model, and nothing in there means anything. Like, we look at this, fundamentally, ultimately, these labels are just magic strings. They're just magic strings. And they say, our data is just JSON. Your data is never just JSON. You're always imposing external semantics. But that means if you want to use it, That means you actually have to go in there and apply these and hand code these again and again and again because they don't come with the data, because we're exchanging data and not information. So let's look at this a little bit, because in that JSON payload, we have an identifier, 0812979796. It is a book. We're going to start to take this apart and put this together in a much more powerful way. We have another statement, because we can think of every single name-value pairs as a single fact. That's a book. It has a title. This is the subject. This identifier's name is Elizabeth Windsor. Title is Queen. 35626 is an author. 35626 wrote that identifier, which is the book. This identifier has a name, has a title, all of these things. We have three parts to each fact. A subject that we're talking about, some kind of relationship, and a value. Sometimes the value is a literal, sometimes it is a reference. Subject, relationship, value. We call that a triple. So now instead of name-value pairs, we've got name-value pairs on steroids. Three things. But this is still just data, because none of those words mean anything by themselves. But what we learned with the web is if I can have an identifier that means that row in the database, and that is a strong, globally unique, shareable, resolvable identifier, then we can identify things that aren't in a database. We can identify concepts. We can identify terms in a vocabulary in an unambiguous way. And so what happened in the late 1990s was we started to standardize something called the resource description framework. And the resource description framework allows us to add that metadata in, add that context in. And it solves a lot of these integration problems because we have data that exists in a number of formats. And the reality is, as soon as we start trying to integrate data, we have to deal with data heterogeneity problems. We have syntactic heterogeneity. In other words, are the syntax of the serialization compatible? We have structural heterogeneity. Are the shapes compatible? And if you've ever tried to put a tree or a jagged hierarchy into a relational table, you'll realize that can be a challenge, right? We have semantic heterogeneity. You use a term, I use a term. Do we mean the same thing? And we also have identity heterogeneity. In other words, you have an ID in your database, you have an ID in your database. Are you talking about the same thing? Now, REST, resources, and URIs give us these last two. And this idea of RDF with these triples gives us structural and solves that structural heterogeneity, because it just becomes, every fact becomes a node in a graph. And anything can be represented as a graph. A table, a tree, a hierarchy, a graph, all of these will fit. And then we've also got like standard serializations and things like that. So think about these ideas as a graph. And as soon as you do, and as soon as you have strong identity, when you want to connect data, I have a subject with a strong identifier, and my identifier, by the way, is w3id.org/people/Michael. I have a birthplace, and I actually have a URI that identifies what this term means, and my birthplace is Wyoming. If I learn another fact about that resource that happens to be me, all of a sudden, I don't have to write any code at all. The data just snaps together. And you can instantly connect a new data set to enrich what you already know, and that's a powerful capability. Because now we're starting to be able to present our data in a way where it just connects. So we can start to add this in here. And one thing we can use is XML. I can say this is a URN, ISBN. I'm now actually specifying this as a URI, as an ISBN. And my concept of a book, it's not a magic string anymore. It is very specifically, in this schema.org vocabulary, a concept of a thing that is a book, right? And I can express all of these things. When I say title, I mean a Dublin Core title, which means the title of a published work. And when I say these other titles, right, I have this concept of a job title. And so now all of this, not only can the data in our database be identified as resources, these terms that we're using are identified as unambiguous resources. And of course, this right here, this is ugly and verbose. Who's like, oh yeah, I love XML? It is cool. It's underrated. But you are an outlier. You are the only person who raised your hand. But there is so much power in there, but it's a lot of work it's like Vim, right? It gives you superpowers, but it's going to take a long time to get those superpowers. And it's a whole lot easier to use Nano or VS Code or whatever else. And this right here, this is RDF XML. This is even uglier and more verbose. Not only that, but URIs are long and big and inefficient as database keys, right? We don't want to do this, right? This doesn't make sense. This is not very optimized for our database storage, but it doesn't really matter what's happening in there. It only matters what comes out. And so, we would rather do things like this with our database, which is totally fine. It's just once it crosses that threshold, that's when it starts to become useful and valuable. And of course, with the exception of you, most people will say, yeah, but XML is kind of, and JSON's awesome. I mean, it's simpler. It is simpler, but you lose a lot of that simplicity. JSON is lightweight and elegant, and there's better tooling for it. But it's still, but remember, information is just data with context, so let's add context. And this gives us something called JSON LD. JSON for linking data. And it allows us just to add that concept. And it became standardized as a new developer-friendly serialization for linked data. So this is another piece of our stack. We have REST, we have URIs, we have the resource description framework, and now we have JSON LD. So we can use JSON the way we love it, and we can turn our JSON into JSON LD very easily. In fact, you can turn your JSON into JSON LD modifying 0 bytes of your JSON payload. Like you can do it with 0 edits. Now, one of the challenges that has historically been around with any kind of integration at scale is you have to get everybody in the organization to agree on what the things in our world are and what we're going to call them. And we learned something a long time ago. We learned something about 20 years ago that in an enterprise, when you start talking to different divisions, they have a different ubiquitous language. And so we think about that as where these boundaries are. And if you're going to try to get the entire enterprise to agree on a single ubiquitous language, it's not going to happen. And this is one of the many reasons the data warehouse approach failed us, because they rely on global consensus. We have to agree on what we call everything and what everything means and what the rules around these things are. But linked data is founded on the same principles of the web. And there are 3 core assumptions. Number 1 is AAA. Anyone can say anything on any topic. And this has even more profound ramifications in the web of data, because it means that our architecture has to allow an individual to express a piece of data about some entity in a way that can be combined with data from other sources. Now, this doesn't mean you have to trust everybody. In fact, we've been kind of playing with different models to build these broader data structures for years. I remember some time ago, if you went onto Google or Bing, because they both had little knowledge graphs under the hood that they were trying to feed with what was on the internet, if you said, who invented running? It would come back because somebody as a joke one day put on the internet, oh, running was invented in 1612 when Thomas Running tried to walk twice at the same time. And it would happily give you that answer. So we don't have to trust everything, but it does require realization that our subjective view of the world isn't the only valid perspective necessarily. And it also means that we could take an open web of data and dynamically define our perspective of truth in any given context. So you and your domain have your context, you and your domain have your context, and these worlds can look different, but we're starting to define our data in a way that you can ask different sets of questions of the same set of data and get the meaningful answers in your world. The second one is the open world assumption, which basically states that there is always more that can be learned about a subject. And the knowledge can come from anywhere. Like when we create a relational database, I say there's 25 columns in my table. And I'm essentially asserting there are 25 attributes for whatever the key is. So maybe this is a person attribute. Maybe this is a person table, and we have 25 columns: first name, last name, email address, phone number, street address, city, state, postal code, whatever. Can I be described in 25 things? Do I have 25 attributes? Is there even any number of attributes? Or can you always come up with more? And that's the open world assumption. And that's so that's the kind of cool thing, because we're talking about connecting data. We're talking about growing these webs of data in the enterprise beyond, spanning all these application boundaries. And RDF is designed to accumulate data and accumulate knowledge in a very straightforward and scalable way. The last one is this, the non-unique naming assumption. That basically we can use different names to refer to the same things. And we can even describe the same thing in different ways. Now, these are the messy realities that we live in. But when we start to embrace them, and we start to think about our data in terms of the reality that it's in, like, everything starts to change. But how do we start to model this? How do we start to actually put this into action? Let's start by talking about building vocabularies. Because the first thing that we have to do is, if we have a term, maybe we have a column name in a database, or we have a name part of a name value pair in a JSON payload, we just have to be able to express it unambiguously with a URI. This is one approach to do it. In this case, this is my organization. This is the domain that I own. It's the example domain. The IETF owns it, or the W3C owns it, or somebody like that owns it. But we have a scheme. How do we interact with this? It's already telling us, how do we interact with this resource? Here's the scheme. It uses HTTPS. We have an organizational namespace. This is called an authority. And then we've got some kind of partition. And then we've got a term. This is one way to do it. Now, I can create these URIs and start using them as terms, even though if I type this into a browser today, nothing might come back. And we think of that as a broken link. We want something to be there, but it's not broken. It's an identifier, as long as we keep this a reserved term. So ideally, we want, if somebody looks this up, it should give you some meaningful information about that. Another approach, so you can use a scheme like this. This is one recommendation. Another suggested scheme that you can use is this, right? We use the fragment identifier for the term. And then this way, you might not have something specific for this term as a fragment in this resource, but if somebody looks it up, you can get some general information. So the first priority is strong names for things. And like I said, they don't have to be resolvable yet. It's not a broken link, but ideally they should give a response, and something like this can start to accommodate that. Now, we've already done this. We've already given most things a name. I know some people, I've talked to some folks who are in the mainframe world, and a lot of these mainframes have really messed up, like, column names in DB2 and things like that. Yeah. But even that is valid. It's just not very friendly. But we've already done that. We're just making it explicit, and it doesn't require reinventing everything. And so as part of the broader suite of standards, we have something called the RDF schema language. Now, when we think about schemas, we usually think about database schemas. But remember this idea of an open world. There's no set of properties for anything. And RDF is about graphs. RDFS is about sets and set membership. So RDFS extends RDF because we're just building a new set of distinguished resources into the language. And it's the same way in a programming language can be extended by adding new language level keywords. At one point, Java didn't have a weight, and then we added it, and now we have that capability. So in RDFS, we have four concepts. We have a concept of a class, which is not necessarily what you think of in the OO world. A class and a subclass in OOP and RDF, they have common roots, but they differ in key ways. So this is a class in terms of like a taxonomy. Like, I am a person, I am a speaker, I am a magician, I am a skydiver. I can belong to all of those sets. And just like something can be a part, it can also be a product. And so it can belong to both of those sets. You can belong to multiple classes. Now, a subclass is where we sort of narrow this. Like, I have a A performer is a broader class of people or animals. I mean, there are performing animals, I guess. A magician is a subclass, is a subset of that. It narrows that down. And then we have properties and subproperties. So we can say something like this. Author is a class. Author has a label. So RDFS gives us label, it gives us type, it gives us class and subclass. Author is a subclass of person. So we're saying that if I say Michael is an author, I can ask the data set, show me all the persons, and I'll show up, even though you didn't say I'm an author or I'm a person, but we're defining that relationship, that taxonomy. And so now we can start to make statements about me, and we can start to do interesting things. So a performer is a class, magician is a class, a magician is a subclass of performer, Michael is a magician. And now we can actually infer that I'm also a performer. Yeah, Michael's a magician, Michael's a name, and a name is a subclass of this label. The label, because again, like the URIs maybe are not what we want to show the user, but RDFS gives us this concept of a label. This is what we're going to show to a human being. And so RDFS labels a really key one. It's a printable name, and the comment is basically the information for readers of the model. So not only does the meaning of all these things be part of the model, the documentation becomes part of the model. So if you look at any of these vocabularies that exist, like the Dublin Core metadata, it has the vocabulary belongs to the identifier, the label, the type, and the definition. So we have RDFS label, RDFS comment. And that's just part of this. And so RDFS becomes another piece. Now, as I'm going through all of this, talking about classes and subclasses, properties and subproperties, and RDFS type, and RDFS label, and RDFS comment, it starts to sound kind of complicated. It's a lot of work. It's easy to just say, oh, I'm going to call this, this, and that. I'm going to use semantic strings everywhere. It sounds difficult, but surprisingly, a lot of people have been doing this as a volunteer effort, unpaid, in their spare time, because they're starting to realize the power of connecting data sets. And one such project took place some time back where they said, hey, we have all of this text in Wikipedia. What if we were to go and take the human readable Wikipedia and turn it into one of these data sets that anybody could have and connect to their data if they want to? So they started decomposing Wikipedia and building these RDF facts, these RDF triples. They built a vocabulary around all of these things. And DBpedia contains about 9.5 billion triples, 9.5 billion facts and counting. And this was in 2006. Now in 2007, a bunch of people said, hey, this is really cool. And it'd be even cooler if I link my data to what's in DBpedia, because now I have everything I know, and I can ask questions not just of what my data set is, but also everything that's in Wikipedia. And I'm connecting those two systems that are typically very hard to connect. And thus began what they called the Linked Open Data Project. And so a bunch of these data sets got projected into RDF with vocabularies, and they started cross-linking these things. And nobody here had to coordinate with anybody else. I'm just expressing my data, and from time to time I'm expressing, oh, by the way, this thing is the same as that concept in DBpedia, which means that if you understand what the concept in DBpedia is, and you understand what the concept of DBpedia is, then this and this connect instantly. And we don't have to go through DBpedia anymore because they're just identifiers. There's no like integration system in the middle. There's no application. It's just how we're expressing the data. And it got bigger and bigger and bigger and bigger. And these data sources can be integrated as fast as they come online. And this is just public data. And I'm not saying necessarily you take all your enterprise's data and you turn it into public data and make it part of this project. Like if it's valuable as public data and you want people to use it for the public good, great, link it to this. But your data is still private. Your data still needs to be secure. And nobody's saying make it all public, make it all accessible. I'm saying use these tools so that if this is your mess of enterprise systems in your organization, they connect as easily and as powerfully and as automatically as these. Because All of these are connected now. And you can ask questions across all of these sets, and nobody had to write a single line of integration code to make that happen. And this is, like I said, this is just public data. So our metadata can go beyond just semantics and meaning, because RDF allows us to describe anything. And so there's another standard out there. We have RDF as a standard, we have JSON LD as a standard, we have RDFS as a standard, and we have another one, this thing called shackle. Because when we have data, the reality is, open world, that's a nice story. Anyone can say anything about anything. That's a cool story, but like, there are rules in my business, Jack. Like, this has to be valid, this has to be correct. Data value, data validation, we want to make sure user input is valid, we want to be able to validate that. And so we can't just, this assumption is great and all. And this introduces another thing called shackle. It's the shapes constraint language. And again, we use the same set of standards. We can be very specific. An account has a last name, it's a string, and we have to have at least one and at most one. We have a social security number, and it has to follow this format so we can express this. And this is a standard. So anybody who understands the standard now understands your business rules. How many times have you added validation to an application? Because you want to do client-side validation, so I coded all my client-side validation in the client, just so I get that feedback. But I also have to code the server-side validation on the server. I've got to code that twice. Now it could just be part of the data. And it makes connecting those data sets even more valuable. What about these last two? Access and security of the data is a responsibility of the data layer or the personal data vault, not managed by the applications. Applications are allowed to visit the data, perform their magic, and express the results back to the data layer. Again, I'm not sure I fully agree. Like, that's a nice vision. That's a nice someday vision. But we're not someday. I don't know. Who here exists in the land of the magical land of someday? We live in today. And today, we have applications everywhere. And that's the cool thing. We can leave our data where it is. We can get our APIs to at least a level 1 on the Richardson maturity model. We can start to build these vocabularies. We can over time build these things. And sure, we have concepts. These are cool concepts to check out. Solid is a social online linked data project. But basically, it's a way of creating social networks where instead of saying, here, Mark Zuckerberg, here's all of my data. What else would you like to know? Go ahead and just install cameras and microphones in my home and in my car. And yeah, you can follow me around and get real-time updates on where I am in the world and turn on my microphone. It's fine. Yeah, here's my contact. Here's my address book. Like, we could do that. Or that data can be entirely ours. And if we choose to participate in that social network, we can give them access. And if we choose to revoke that, it's our data, we take it with us, and we go to the next one. So if you were in Twitter, and then you're like, Twitter's not as cool as it once was, I'm gonna go to Blue Sky, well, everything falls apart, and you gotta build it all up again. If you're watching Netflix, and you've built up all of this data about the shows that you like, Netflix owns that data. Imagine that was your data, and then when you leave and you go to Amazon Prime or Disney Plus or any of these other ones, you can just come right in and say, oh yeah, here's my viewing preference data. I'm choosing to share it with you. And now you don't have to train the algorithm anymore. And you can leave this data where it is. But there's a lot of different ways to do this. You can leave the data where it is in the applications right now. But what you start to get is as you're making this data in these formats, in your systems, it starts to connect. And with very little effort, you're starting to get a growing enterprise knowledge graph. And enterprise knowledge graphs are powering the most innovative companies, right? This slide is 5 years old now. And it is huge and it's powerful. And knowledge graphs are solving a lot of seemingly intractable problems. But the thing is, in terms of this data and where it is, like, this is the progression that we've gone in over the last 70 years, right? We had computers. And then as we started standardizing on TCP/IP and DNS, we started to be able to connect these computers. And so physical location at this point starts to become irrelevant because it's all on the network. And then as we have our documents and they're all isolated and siloed, but when we moved to the web with HTTP and HTML, the containing file system started to become irrelevant because it's just the web. We're just linking documents all over the place. And now we're in this place where our data, our entities, our concepts, they're all still siloed. But when we use RDF and linked data, we can start to connect and express these things. And our databases and applications start to become irrelevant. And we just have this web of data. And so we're currently here, but these standards are going to allow us to go here. And again, this doesn't mean put all your data on the World Wide Web necessarily, but this is you can get the micro scale of the macro possibilities. And so there's some interesting standards out there. One of them is R2RML. Maybe I've got a legacy application that has a relational database somewhere. It doesn't even have our API, let alone one I can modify. Well, that's cool. This gives me a layer over my relational database that allows me to project whatever's in there into RDF. And you can use RDF XML or JSON LD or Turtle or whatever else. And so we have that new linked data endpoint. And if you have a system that gives JSON, it becomes trivial to turn that into JSON LD. So again, you're moving incrementally in that direction of linked data. You're moving incrementally in the direction of being data-centric. And that starts to solve so many challenges that we're dealing with. And when we have this maturing data, really radical things start to happen. Because we start to be able to express not just data, not just information, but knowledge. We can express even more. So RDFS gives us two things that are kind of interesting, called the domain and range constraint. And it basically allows us to type data by usage. And so this is a very formal way of kind of expressing this that I'll show you a concrete example. That'll be a little better. I have a property. And the property has a stage name. I have a stage name because I am a professional magician. And I've chosen to adopt a stage name. Now, not everybody has a stage name. A stage name is something that a performer has. So has stage name is a property. Property, the has stage name is the RDF domain of performer. That means if I assign this property to a resource, it means I am performer. I can say, so the domain is what that implies, what that property implies, and range is what that should be. So I can say, performer is a class, magician is a class, magician is a subclass of performer, Michael is a type of magician, Michael has a name of Michael. So I can express all of this. Or I can define more information about the vocabulary. And so as long as I say Michael has stage name Michael Carducci, then I don't even need to say that I'm performer because that is implied. Now, that is another one of those areas that it's worth talking about because it can trip you up. Because sometimes you're doing these things and you say, okay, I'm going to create a pizza. I'm going to create a vocabulary for pizza. And so my pizza has an attribute of a pizza, has topping. Pizza has topping chicken. Pizza has topping onions. Pizza has topping, I don't know. And so I can say, well, then the has topping property has a domain of pizza. And then I'm making another one, an ice cream sundae. And I'm saying, you know what? I have a term for has topping. My sundae has toppings too. So my sundae has a topping of chocolate sauce. My sundae has topping of a cherry or ground nuts. But because I've defined has topping as the domain of pizza, I just said my sundae is a pizza. And so you want to be careful with some of these things. And in fact, schema.org, which is an attempt to give a standard common set of terms that we all don't have to agree on, but we can use to connect our terms with schema.org, when they talk about expected type, they're a little more vague in how this works. They don't use RDFS domain, they use domain includes as a custom term. And then in this case, you can go in and say, you know what, domain includes is the same as domain. But let's keep going because we're running out of time. I think we have like 3 minutes left. Is that right? Yeah, so I better keep going. And then we start getting into knowledge, and we could express really powerful things, right? Plato, born in 428 BCE, started thinking about way back in the day in ancient Greece, what does it mean to know something? What is knowledge? And he said, knowledge is justified true belief. So I'm going to tell you a fact. I am married to Kate. I can justify that fact. Here's my marriage certificate. And if you believe me, you also know this fact. I don't think that reference lands in India, but we'll keep going. Let me tell you another fact. My best friend is Draco. You know 2 facts. Let's see what else you know. Is Kate married to me? Yeah. That fact is also true, and if you happen to believe it, you probably believe it, but how do you justify it? How do you make that a justified true belief? Because I never told you that. I told you I was married to Kate. So how do you know that Kate is married to me? Yeah, well, the marriage certificate. That's true. But more broadly, the relationship of married to, if I'm married to her, she's married to me. That's how it works. Now, the data doesn't tell you that, but you know that. Okay, how about this? Am I Draco's best friend? No idea, right? These relationships have different behavior. And now we start getting into logic. And this is what the ancient Greeks and the philosophers struggled over for a long time, because they decided that if you're going to use what they called the tripartite test, justified true belief, you can't just say, I just know, or you can't just say, that's just how it works. Like, it doesn't compute. So knowledge is more than storage and retrieval of facts. And so there's even another cool tool in there. And again, you don't have to do all of this at once. It's very incremental, but it opens a path to really powerful capabilities, writing 0 code. Your data just gets more powerful and it just connects. So there's another standard in this world called OWL, the Web Ontology Language. I don't know how that stands for that, but it does. There's a lot in here. But what we can do is we can say Michael is married to Kate, Michael's best friend is Draco, but I can start to express things. I can say married to is a symmetric property, which means it works both ways. So Michael's married to Kate, and so we can ask the data set now, even though it's not in there, we never inserted that record, we can say, hey, who is Kate married to? Michael. And we know what to do. And so there's a lot of cool things in here. You know, we can really start to formally express how the knowledge in our organizations and our systems work. And things like data integration just go away as a problem. And we have systems that can answer questions now that we don't even have the data for. And so, you know, one interesting thing is Google's making very heavy use of linked data and JSON LD, and it's what allows them to integrate countless systems. Like they didn't have an army of programmers like write all this brittle integration code to integration with every little custom system of every hotel and every airline. They just said, you want to be involved? Give us data-centric data. You want to show up in the search results? You want to show up in the online booking for your hotel? You give us data-centric data, and you're in. You want us to write code to integrate with your system and your custom proprietary format? It's out of luck. And so doing this, you get all of this data, however it's expressed, and it just connects. Because I can say, you can just say, here's all my data. By the way, this term means that term in your world. And once it's in there once, it's there forever. You get that network effects. Now, there's a whole set of standards and technologies and tools to deal with all of the real problems like proof and security and trust. But what makes this really, really, really powerful is we know generative AI is cool. We also know that at the end of the day, you take all the fanciness and all the cleverness and all the bells and whistles away, it is a text synthesis engine that is doing nothing but guessing the most probable next word, next token in the response. But what if we could take that and connect it to our organization's data, to the organization's knowledge? So there's a guy named Tony and I'm drawing a blank, I'll post it somewhere. He showed a very quick demo probably almost 2 years ago now, just after GPT-3 came out, showing how this can work. Well, I'll link to that a little later on, but he just shows how you can connect directly to these knowledge graphs. And it's cool stuff. And Sparkle gives us a federated protocol and query language for asking different questions. Like the solutions to these problems are coming, and we can evolve or be disrupted because right now we're spending 35 to 65% of IT budgets on integration. Data-Centric makes that free. Cost of change becomes reasonable. And I know we're 1 minute over time. I want to thank you so much. It has been such an honor and a pleasure to be at this event with you. Thank you so much.